Hi everyone. Today we're excited to have Dr. Fernando Carcaboso, a postdoctoral researcher at NASA Goddard, speaking to us about his work on characterizing suprathermal electrons. So Fernando completed his PhD at the Universidad de Alcalá in Spain in 2021, where he researched the global topology of flux ropes and structure of interplanetary coronal mass ejections, as well as their influence on the propagation of solar energetic particles. He's involved with both the Serpentine project, which aims to address questions about the origin of the solar energetic particles, and also the energetic particle detector instrument on board solar orbiter. So for today's seminar, he'll be presenting his work on the advantages of characterizing the suprathermal electron pitch angle distributions in ICMEs and long-term variations. So we're really excited to learn more on this topic. So thank you, Fernando, and we're ready whenever you are.
Okay, thank you very much for the opportunity of giving this talk, and also thank you very much for arranging this seminar, which I know is not easy. So I have called these advantages of characterizing the suprathermal electrons pitch channel distribution, but in fact, what I'm going to explain here is based on a methodology that could be applied to anything that is space distributed. So it can be photons, it can be any plasma parameter where you have multiple points of observations and so on. But yeah, as I said, this is only focused on the suprathermal electrons, and especially with interest on the solar wind analyzers on board stereo and wind, and also ACE. And I will try also to tell what the futures plan are with PSP and solar orbiter. I have divided my presentation into three main blocks: the introduction, data analysis, and summary. Within the data analysis, I will focus on three different studies. One is mainly focused on the paper I published in 2020. I will tell about it, and the rest are part of my PhD thesis that is publicly available, and I will put the link later if you want. So as an introduction, I guess most of you know, but I'm going to explain what the solar wind and the interplanetary magnetic field are. So we have the theoretical Parker spiral. Due to the emergence of the solar wind plus the rotation of the sun, Parker postulated that the interplanetary magnetic field is frozen within the plasma, and this compose Euclidean spiral that is just propagating in the heliosphere. The thing is that you can also propagate in the 3D space, and also added to the differential rotation of the solar wind, it provides different behavior of the spiral in depending on the latitude. But the thing is not as good as theoretically could seem. In fact, the interplanetary field conditions are much turbulent, which may hampers the possibility to propagate easily to the particles, especially in the suprathermal and quasi-relativistic range, and I will talk about this. But we don't only have the Parker spiral. We also have different regimes of the solar wind. So we have fast solar wind and a slow solar wind, and the interaction between these, they form what is called the stream interaction regions. And with this, many things happen. But we also have different polarities in the magnetic field topology. So we don't have a monopole. So the sun behaves mainly as a dipole, and the two different polarities create a neutral line that, when it's propagating in the interplanetary medium, produces what is called the heliospheric current sheet, which is a very thin, or supposedly very thin, region where there are particular behavior of the plasma, especially its large current. So also, apart from this overview, we also have eruptive phenomena as the coronal mass ejections could be. So there are people claiming that there are two possible mechanisms that explain the release of the coronal mass ejections. What could be the shared arcade method on the middle, and then the traditional flag strobe. So we have a flax tube that is connected to both lengths, and then there is a reconnection in below that is forcing the flax strobe to propagate to the interplanetary medium. When the coronal mass ejection reaches or propagates through the heliospheric, to the heliosphere, we have the interplanetary counterpart, which is denominated the interplanetary coronal mass ejection, which also has some properties. So we can define a standard ICME as with 4 different regions. So we have the shock when it's supersonic. Then we have a turbulent region, which is denominated the sheath. Then we have the magnetic obstacle, and then what I denominated in my paper post ICME, which is a regime that doesn't have the properties of the ambient solar wind, and it doesn't have the properties of the magnetic obstacle. So it's a mix of both. Going to the suprathermal electrons, that's why I'm here talking. We can have 3 different populations in the solar wind regarding the electrons, or even more. But by looking at the thermal energies and suprathermal energies, we can distinguish 3 main populations, which are the core, the halo, and the strahl. Both core and halo are isotropic, but they follow different distribution functions. So the core could be fitted to a Maxwellian distribution, while the halo is broader and also can be fitted to a kappa distribution. Meanwhile, the strahl population is the suprathermal population, just above the thermal energy, which is 60 electron volts for 1 astronomical unit, and is the field-aligned beam. The suprathermal electrons, they have different properties. One of them is that they have low energy, which also provokes a small gyroradius. They are always coming out from the sun, which provides information of directionality, and from that we can extract the data product, which is called the pitch angle distribution. So the pitch angle distribution results from comparing the direction of the magnetic field and the intensity of the suprathermal electrons. So here we have 4 different scenarios. In case A and C, we have the suprathermal electrons. Maybe I can turn the laser. Okay. In case A and C, we have open magnetic field lines with different polarities. So in case A, we have negative polarity, inward polarity. So the suprathermal electrons are coming in antiparallel when they cross the observer, and in case C, they are coming parallel to the observer. So we see the pitch angle distribution with cosinus 0 or with cosinus 1 or -1, depending on the polarity mainly, if we don't have any kink in the interplanetary magnetic field. In case B, for example, we have a closed structure. This could be the case of a flag strobe within an ICME that is still attached to the sun, and we can see the injection of the suprathermal electrons coming antiparallel and parallel to the magnetic field. So we see the addition of the 2 strahl populations just in the distribution function. And in case D, for example, here would represent a completely detached magnetic field lines, and there is no injection of the suprathermal electrons, and what we see is the smeared population just coming from the surroundings of the magnetic field. So we see an isotropic flux, mainly core and halo population. We also can, as I mentioned, detect the kinks of the interplanetary magnetic field, which is called now switchbacks in the interplanetary medium. So when the suprathermal electrons are propagating towards the sun, we can tell, or in principle, that there must be a key in the interplanetary medium, and that provokes the suprathermal electrons going towards the sun. So the interplanetary magnetic field is very complex. We have many variability, we have turbulence, and the suprathermal electrons are here to help us to unravel the topology and the conditions of the interplanetary magnetic field. So the first study that I'm going to talk about is the suprathermal electrons characterization and long-term variation of isotropy and bidirectionality, and also the long-term variation of the anisotropy. So this study is based on the pitch angle characterization that I performed in the 2020 paper. So when we see the pitch angle distribution in the solar wind, we often see this color mesh plot, which represents the distribution function in logarithm scale in the z-axis with respect to the angle and in time. And we can identify by eye some features in the pitch angle distribution. So we can see some bidirectionality here. Maybe this is a bit of lost cone. This is counterstreaming. This is a simple strahl, so open magnetic field line, some bidirectionality here with more intensity here. And if we gather the most common pitch angle distributions in the solar wind, we can identify these ones. So we have a simple strahl with open magnetic field line, with inward polarity, outward polarity, counterstreaming, which would be in principle the addition of both strahls. We can also find pancakes, lost cone, which is strahl plus the converging lines provoking the suprathermal electrons to reflect. And we also can find butterfly, isotropic flux. And here I will focus on these ones, which are the bidirectional. So bidirectional means by itself that they are coming from both directions. So it would imply these topologies and also the isotropic. In order to characterize the pitch channel distribution, I use the Legendre polynomials up to the fifth order. So the Legendre polynomials results from solving the Fourier transform for spherical coordinates. And I just used the data provided by the teams, the pitch channel distribution data. So I didn't need to propagate all the fittings just by myself. This is something that is not new. Many people have done that. So for example, Sanderson et al. In 1983, for SCPs, and Nugget and Lario in 2016. There are many examples. And also for the suprathermal electrons in the magnetosphere, there are also some cases, and with better statistics actually than what we can find. Better statistics, I mean better cadence, and with different points of view in the magnetosphere. So for example, Chen et al. In 2014 show a method to characterize also with the Legendre polynomials. So the Legendre polynomials have this shape. We can see that the terms from 0 to the fifth order, the 0 order would correspond to the mean value of the pitch channel distribution. Second and fourth are symmetric with respect to the y-axis, and the rest are anti-symmetric with respect to the 0, 0. In a first approximation, we can tell that the bidirectionality of the electrons is equivalent to say that we have a symmetric pitch angle distribution for positive coefficient. If we have negative coefficients, we would or may have a pancake distribution instead of a bidirectional. So we need to quantify the predominance of symmetry. We want to analyze the bidirectionality. For doing that, I use the signal processing analysis, a very well-known measure of the signal, and which is the signal to noise ratio, which is the relation between the power of a signal and the power of the noise. I was considering signal the second and the fourth coefficient, which quantifies the bidirectionality with respect to the P1, P3, and P5, which I consider noise to these purposes. But we also need to characterize the anisotropy. So if we go back and see here, the A0 term would also be symmetric with respect to the y-axis, but we need to get rid of all isotropic events that we may find in order to identify the isotropic events. So for doing that, there is something called the ripple of a signal, which is the root mean square of the contribution of the harmonics, considering harmonics the terms with greater and greater than 0. So from A1 to A5, and divided by the mean value, which is A0 in this case. So how do we identify the isotropy, and why is produced the isotropy? So the isotropy, as I mentioned, is mainly halo population, also core sometimes, and the anisotropy which corresponds to strahl population and also reflected the strahl population. So the mechanisms that produce the anisotropy could be focusing of the also converging lines for the reflection, the fact that the sun is producing suprathermal electrons all the time, and to produce isotropy, we have scattering, total detachment of the sun, and some others. Here we have an example of a heliospheric current sheet crossing. You can see here shaded in yellow, and where the magnetic field strength just drops, the plasma beta increases, and the suprathermal electrons here just decrease and become isotropic, the entire pre-channel distribution. Here I have the ripple, which is the anisotropic coefficient, and you can also see that it varies here. And I define a threshold that I'm going to explain now. So whenever this is below the threshold, it becomes red. How did I identify the threshold? So I based my study in previous studies as Crooked et al. That they had a method to characterize the anisotropy, and I obtained similar results, and they got for wind, if I recall correctly. And I compared the anisotropic coefficient with respect to the plasma beta. So there is an anti-correlation between the plasma beta and the anisotropy of the suprathermal electrons. So the higher the plasma beta, the less anisotropic the suprathermal electrons behave. And in order to define the threshold, I took, some of you may know what this is. This is the first order anisotropy. So whenever you don't clearly distinguish whether the electrons are coming from one direction or the other, that's where I defined the threshold, which is more or less a 15% in the ripple. So above that threshold, I consider an isotropic flux. Below that threshold is isotropic to me. In order to identify, then I need to filter first the bidirectionality. I need to filter first what is anisotropic and what is isotropic. So once I have that, I can tell, okay, this is isotropic, this is bidirectional or not. Why do we have bidirectionality in the solar wind? It could be due to the presence of a closed loop, for example. So if we are linked to the sun, for example, in the case of an ICME, we have the counterstreaming electrons. Also, we can see that in converging lines in the SIR's proximity. So we could also have the mirroring producing lost cone. And why, for example, in the case of the ICMEs, we don't see the bidirectionality, mainly because of the reconnection, erosion processes of the magnetic field lines, or because actually we don't have a flux strobe structure. So for instance, we could have a complex ejecta, which is not necessarily attached to the sun in both legs. Also, they could be originally open magnetic field lines. So many things. So, for example, we have a blob, and it's not necessarily attached to the sun. In order to define a threshold to identify what is bidirectional and what is not, I took a sample of ICMEs with good and clear and long pitch angle distribution showing bidirectionality. And I compared that to the solar wind conditions, which is the blue one. As you can see, the signal to noise ratio, the second and the fourth coefficient, is greater for the case of the ICMEs, which shows the pitch angle distribution is more symmetric in the ICMEs with clearer bidirectionality. And in the case of the ambient solar wind, what we mainly have is open magnetic field lines. So we don't see any symmetry in the pitch angle distribution. So that's why it's below 0. So I wanted to make sure that what I had for the analysis here was bidirectional. So I defined a threshold close to the mean. I didn't take the mean, I took the median, which is 5.8 decibels. And above that, I said, okay, I'm going to consider this as bidirectional electrons. So I just analyzed the long-term variation of the isotropy and the bidirectionality. And there are some remarkable things. So here I'm calculating the average, or the time percentage in a month of the different pitch angle distributions for bidirectionality and isotropy. Isotropy in the case of stereo A, isotropy of the stereo B, bidirectionality for stereo A, and bidirectionality for stereo B. As you can see, there are some oscillations in the isotropy. This could be produced to the wavy behavior of the heliospherical sheet in interplanetary medium. And also it could be due to the radial dependency with the of the suprathermal core breakpoint. So whenever we reach that point, the suprathermal electrons is not suprathermal anymore. It becomes part of the thermal population. And then we have halo isotropic population. In the case of the bidirectionality, we can see that it's increasing with the solar wind, as well as the number of ICMEs and the time crossing of the ICMEs. And if you notice here, there is a remarkable peak in both isotropy and bidirectionality, just coinciding with a sudden change in the tilt angle of the heliospheric current shield, which is the black line. So this could be just explained by the more frequent crossings, so through the heliospheric current sheet in the case of the isotropy, but for the bidirectionality enhancement, I have no answer. So maybe you do. Please let me know. I also analyzed the anisotropy variation. So not just looking at the threshold I defined, but the long-term variation of the anisotropy. And I compared, so this is ACE measurements for 272 electron volts, which is the main product they provide for the pitch angle distribution, and compared that to the sunspot number. As you can see, the anisotropy is increasing with the solar cycle and is decreasing in the solar minimum. And it also catches the two peaks that we found in this cycle, which is from 1998 to 2010. And I wanted to know why these variations are happening. So is it because we have less frequent crossings through the heliospheric current sheet? We have more activity, so we have more ICMEs, so which implies more anisotropy, or what? So I analyzed the anisotropy variation with different things. One of them was the energy. So there is an energy dependence of the anisotropy. We have larger anisotropies for larger energies, but is this happening all the time? I don't know. I wanted to figure out. So I looked at the long-term variation of the anisotropy for both stereos for the different energies. And you can see that systematically, almost systematically, the higher energies, the higher energy channels were presenting more anisotropy than the lower ones. But it's not always the case. So there are some periods where, so this is like really averaged. So it is not just a matter of hours. It's even longer. There are periods where the low energy channels, for some reason, present more anisotropy than the lower ones. And also, there are some periodic behavior that you can see here that I wanted to understand. And these are all open questions, and so these are ongoing works, and I have answered for some of them, but for some other reasons I don't have any clear explanation. And I wanted to figure out if that periodic behavior was only a thing of stereo, or was it implying more satellites. So I analyzed ACE in the same period, more or less, than the data provided by both stereos. So unfortunately, we lost stereo B in June, July 2014, so I didn't go further. But you can see that the behavior is more or less the same for all the spacecraft. Even there is some time difference between the peaks, so it must be something related to the orbit of the spacecraft, which is happening from the sun and then propagating to them. Also, I must say these are different energies, so there is no channel that matches both ACE and stereo A. So stereo A is stereo and stereo A and stereo B are lower energies than the ACE. So I think stereo was 120 electron volts, while ACE was 272. So it's a bit higher. And you can see that systematically ACE presents higher anisotropy. That is one of the results I found out. But yeah, where these peaks are coming from, I don't know. So in order to find out where they were coming from, I was looking at some magnetospheric connection to different planets, orbital configurations, any kind of approximation. And one of the things I did was the proximity to the neutral line. So I did perform a backmapping based on the velocity of the solar wind. And once you are there, I took the PFSS model to find the foot points, the magnetic foot points to the solar surface. And from there, I calculated the minimum distance to the neutral line. And this is what I got. So for the quiet period, because I don't trust the PFSS model in solar maximum, also because there are other things to consider. So it is not a dipole anymore, the sun during solar maximum. I just took in the solar minimum 2008, 2009, 2007, something in between. And I compared the anisotropy, so the ripple, with respect to what I call the heliomagnetic latitude. And you can see that the anisotropy is increasing with larger latitudes, and it's happening the same for all the spacecraft, and it's becoming lower closer to the heliospheric current sheet. So we have seen previously that one of the characteristics of the heliospheric current sheet crossings is to present isotropy. So it is normal that then if we are closer to the neutral line, we observe lower values of isotropy on average. But was the explanation of having larger anisotropies in larger latitudes and I don't know, more pronounced isotropy here? That's something I have no explanation. So it could be due to the different regimes of the solar wind. So is fast solar wind producing larger anisotropy than slower solar wind, closer to the neutral line. That's something I need to figure out. So to conclude this part, I have presented a method to characterize the p-channel distribution. There are some available catalogs of isotropic and bidirectional periods observed by SWEA that you can find on the paper. The isotropy seems to depend with the radial distance somehow for stereo B, but for stereo A, there is no clear dependency. The isotropy is more frequent in solar minimum, probably because we have more tangential crossings of the heliospheric current sheet. There is a sudden change of the heliospheric current sheet tilt angle, which also coincides with isotropy peak for both stereo. Could it be produced to larger and more frequent crossings through the heliospheric current sheet? And then there is some periodicity of 13 months that seems too much for stereo B case with the radial distance but for stereo A is uncertain. In the case of the bidirectionality, is increasing with the solar spot number, as well as the number of ICMEs, so it's normal. One of the properties of the ICME is to present bidirectionality. The sudden change of the heliospheric current sheet tilt angle also coincides with a peak in the bidirectionality for stereo A. More clear for stereo A, but also there's a clear peak for stereo B. And the anisotropy anti-correlates with plasma beta. That was something already new by, so for example, Crooked et al. In 2003. It is commonly, but not always, higher for higher energies. It is wider. Yeah, the anisotropy cover wider ranges in solar maximum and lower in solar minimum. It is higher with larger heliomagnetic latitudes, and there is also a periodicity of 30 months, which shouldn't be correlated to the isotropy because the threshold is just defined by to identify isotropic periods, but the amount of anisotropy shouldn't be correlated in principle. But there it is. The second study focuses on the interplanetary coronal mass ejections, especially in the isotropy and the bidirectionality evolution. So when I was looking at the ICMEs, here we have an ICME crossing. This is the typical shape of an ICME. We have the shock, we have the sheath, and then we have the magnetic obstacle. So the sheath is a turbulent region, and sorry, there are some noises and I'm getting distracted. So I will start. So we have the shock, we have the sheath, and the magnetic obstacle. The shock is due to the supersonic behavior of the ICME. The sheath is a turbulent region with higher density, temperature, usually because it's being eroded and also compressed, which implies to have a higher beta, and also the isotropy of the suprathermal electrons. Then we have the magnetic obstacle, which is less dense than the ambient solar wind or the surrounding solar wind. The magnetic field usually is more higher than the ambient solar wind, with smooth rotation of the components, low plasma beta, and presence of bidirectionality. As you can see here, I'm representing the ripple, which represents the amount of anisotropy, and the signal to noise ratio, which represents the amount of bidirectionality. But it was really interesting then seeing that what the catalog says that the ICME is seems to be much larger. So you can see that in the rear part of the ICME, we still can find bidirectionality, and this is not lasting for just a few hours. So this is half a day, bit longer, and this is 1 day and a half. So it's much larger than the actual cross of the ICMEs. And still we have some properties of what an ICME could be. So we have some kind of expansion here, low proton density and temperature, and the magnetic field seems to be higher here than previously. So I perform a superposed epoch analysis considering stereo, and there is an ICME catalog provided by the StereoMag team. So I took the transit of both stereos and divided into different sectors just in time. So I divided the into three sectors, the sheath, into four sectors, the magnetic obstacle, and then the rear part, which I call post-ICME, which is, I define 1.2 times the total duration of the transit of an ICME. And why 1.2 times? Because it's the time that takes to recover the nominal behavior of the ambient solar wind, which is represented by this dashed line. I calculated the time percentage of the bidirectionality, as I explained before, by defining the thresholds. And as you can see, the amount of bidirectionality is increasing until the first half of the ICME, and then it's gradually decreasing, but there is a jump here in the post-ICME region. But still, we can find bidirectionality right after the post-ICME, right after the magnetic obstacle. And this is mainly due to two reasons. One of them is the existence of still close magnetic field lines, which are still attached to the sun, so they are injecting electrons in both directions of the magnetic field, and also the reflected electrons coming from the shock. So we have the strahl population being reflected to here, or even accelerated in the shock, and then they are propagating, avoiding the magnetic obstacle to the observer afterwards. I performed the same for the isotropy. So as I mentioned, the sheath is a turbulent condition, which smears the strahl population to become part of the halo population, which isotropicize the behavior of the suprathermal electrons. And we can see that it's gradually decreasing until it drops in the magnetic obstacle, mainly because of two reasons. One of them is that the magnetic obstacle is isolated from the surroundings. So the magnetic field is very smooth, and the electrons can travel very easily without any turbulent conditions, which can scatter the flux of the electrons. And then when going out of the magnetic obstacle, we see an enhancement of isotropy so larger than the ambient solar wind. And this could be produced mainly because of the erosion processes of the ICME. So whenever we have a nice interplanetary magnetic field reconnection, that provokes, among others, the turbulent conditions of the interplanetary magnetic field, which smears the suprathermal population. So as conclusions, the bidirectionality increases gradually with the transit of the ICME. We can see reflection in converging lines, and closed magnetic field lines with eroded in the sheath. So that's why we see an enhancement in the bidirectionality. Then the bidirectionality is increasing until the first half of the magnetic obstacle, and then is decreasing. And in the post-ICME, it decreases gradually until 1.2 times the total duration of the ICME. The isotropy is common in the sheath. It's less common in the magnetic obstacle due to the smooth magnetic field lines and because it's not eroded. And the isotropy is similar, sometimes higher in the post-ICME. The last study was a comparison with quasi-relativistic electrons, especially impulsive events. So the impulsive events are flare accelerated, and people claim to have the impulsive SCPs with a very narrow propagation. So I took the stereo SCPT solar energetic solar electron events, and I took those that were very anisotropic and very impulsive. So we had the two stereos and the solar flare also associated to a type 3 data burst. And I was looking at the time difference using what is called the time shifting analysis for a certain energy between the type 3 data burst and the arrival of the SCPs. And this is an example. So I was taking the type 3 data burst and the onset of the ICMEs on the SCPs, and then looking at the conditions of the suprathermal electrons, especially the anisotropy coefficient. And this is what I got. So this is a very complex plot, I know, and is quite difficult to summarize. But basically, on the y-axis, we have the anisotropy of the suprathermal electrons, and here we have a normalized Parker spiral length based on the time shifting analysis of the propagation of the impulsive events. So is normalized to the velocity, in situ velocity solar wind. So I took Parker spiral, a nominal Parker spiral length. And I also applied an algorithm, which is an empirical algorithm to identify different regimes of the solar wind. So we can see that if the solar wind is coming from an ejecta, from a coronal hole, from a sector reversal or stream and belt. And also I was basing this study to compare with the catalog. So near a shock, within a sheath, within a magnetic obstacle in the post-ICME region, stream interaction region before the stream interface, after the stream interface, or uncatalogued. So most of them are uncatalogued because they happen in the ambient solar wind. But still we can find some features. And this, so you can see that the larger the anisotropy of the suprathermal electrons is, the shorter the theoretical path length of the SCPs is. And this implies that the conditions that may affect the suprathermal electrons traveling may affect also the SCPs. So as conclusion, the shorter estimated SCP path length it is shorter when the anisotropy is higher. These are similar results as reported by Graham et al. In 2018. And there is an unexpected lack of correlation that I mentioned between the propagation, the ripple, and the topology of the structure. So I was trying to find some correlation between the structure and the propagation of SCPs, and I didn't find it. So just as a brief summary, because I wanted to make this shorter, actually like 10 minutes. We have seen three main studies. So the suprathermal electron speed channel distribution characterization, isotropy and bidirectionality in the solar wind, and the anisotropy variations. The analysis of the isotropy and bidirectionality in the coronal mass ejections, and the comparison with the energetic electrons, especially impulsive events. So we have found a method to characterize the p-channel distribution using signal processing analysis and the spherical harmonics. We have seen the variations of the isotropy and the bidirectionality and the variations of the anisotropy in different regimes. In the case of the ICMEs, we have seen the evolution of the isotropy and the bidirectionality. And we have compared the arrival of the impulsive SCPs with the anisotropy of the suprathermal electrons. And this would help us to understand the interplanetary magnetic field topology, especially in the case of the ICMEs. But as I mentioned, this characterization method can be applied to many of the things and have more applicabilities. So I can tell you some other applications that this method has. So for example, calculating the strahl width. So previous study, as the mentioned Graham et al. 2018, were characterizing the strahl width by fitting to two Gaussians and a first order polynomial. But you can actually extract the information just by fitting to the Legendre polynomials and getting the roots from the distribution function. And we get more or less the similar results. And also, if you want, you can apply machine learning classifiers in order to identify the different p-channel distributions that you may find in the solar wind. So for example, I applied this to identify pancake, this should say counterstreaming instead of bidirectional, butterfly, lost cone, strahl, and isotropic flux. And I wanted to see the variation of these p-channel distributions within the solar cycle. So you can still see this periodic behavior due to the change of polarity in the interplanetary medium. You can see the enhancement of the increase of bidirectionality with time, being larger in the solar maximum and smaller in the solar minimum. The distinction between what is with inward polarity and outward polarity is being more smeared here in the solar maximum because the dipole is not well defined as it could be here in solar minimum, and so on and so forth. So as future work, I want to analyze the long-term variation of the solar wind, so characterizing the p-channel distribution for all the available missions, so solar orbiter, Parker Solar Probe, especially to find the origin of those periodicities of 30 months. Also, it would be good to have analysis of ICME evolution, so as they tell a lot of information about the erosion processes of the ICMEs, they can tell a lot, especially for multi-point observations, and to see the angular, radial, and latitudinal different dependencies. And also, I've shown the potential of analyzing the suprathermal electrons with the SCPs. So I developed a type 3 radial bars model that I didn't mention here, but I want to improve that and to compare that with the analysis of the suprathermal electrons, and to understand the connection to the different interplanetary structures, because I didn't find any correlation, and that's unexpected. And that's all I wanted to tell. Thank you very much.
Great, thank you, Fernando. Right, well, firstly, does anyone have any questions, either in the room or online? I can see lots of clapping emojis, not hand raised ones. Well, whilst people are thinking, I have a quick question about the superposed epoch analysis plots that you showed. So yeah, so you said you used all the ICMEs in the stereo catalog. Oh, a bit before then, Fernando.
Sorry,
Yeah.
I forgot to put the numbers of the slides.
Sorry, it was a while.
Which one?
Just clicked past them in the summary.
Okay, well,
Sorry. With the percentages. Yes.
Here?
Yeah. So you used all the ICMEs in the stereo catalogs to produce.
Yes.
I guess, did you have to filter based on certain ones that are in close succession or interacting to produce these plots?
So in the case of the post ICME, what I did, it was if there was any kind of structure afterwards, any shock, any SIR or another ICME, I was just removing that. For the rest, I think I didn't consider anything else. I don't remember. I would need to check, but I think they are all here, and they are 318 events, and most of them are just included there. In the paper, I separated by those with shock and those without shocks, but here I'm just showing a brief summary.
I was also going to ask if you played around with, say, like filtering by the different ICME properties. So say if ICMEs had stronger magnetic fields, does that have an influence on the bidirectioning?
Yeah, I expect to, well, at least to see with the turbulence. So I expect to see less isotropy when it's less turbulent, which is a direct comparison with the plasma beta conditions, basically. So the more turbulent, the more plasma beta you have, the more isotropic electrons.
Okay, thank you. Oh, I think Florian has a question. He's come sat by me.
It's just like a follow-up question and over, yeah. Okay. So, and also like, did you, because I think in the catalog you used, it's basically, so magnetic obstacle, meaning that not necessarily magnetic clouds, right?
Yeah, totally right. So the magnetic obstacles can, so according to Lanyan, who was the developer of this catalog, a magnetic obstacle could be a complex ejecta, could be a single flag slope, a multiple flag slopes. So it's not necessarily associated to a magnetic cloud. So the magnetic cloud is a specific type of flag slope with certain properties as low plasma beta, bidirectional electrons. But no, they are all included. It doesn't really matter if it's magnetic cloud or not.
I would be curious to see the differences between magnetic obstacle and magnetic clouds, because I would expect also like to have some strong difference in the bi-directionality, for instance.
Yep, and I'm pretty sure if I remove those, so I wanted to include all of them because otherwise it would be biased. So I just wanted to have a superposed epoch of a nominal behavior of the ICMEs. And even with that, you still see that the center has more bidirectionality and less isotropy than the ambient solar wind.
Okay, interesting. Thank you.
Thank you.
Do we have any other questions in the room or online? Everyone's been quite quiet. In which case, I've got a really quick final one, just basically for my benefit. You've produced the catalogues of the different characterizations of the pitch angle distributions for stereo. I saw in you've got new work now that also does some that uses ACE. Will you also be releasing those catalogs at ACE?
Yeah, why not? Yeah.
Cool.
Yeah. The good thing about this method is that you can apply more or less easily. So you can have, as far as you have the pitch angle distribution data, you can just fit to the Legendre polynomials, extract the information from there. But yeah, I would be more than happy if I had the time to publish that and to release also his catalog. Not only ACE, but PSP Solar Orbiter.
Yeah, that would be great. Right, well, if there are no final questions, then I think we should thank Fernando again. Thank you.
Thank you.